Hello and welcome to the second part of Module 1 CET 201 Mechanics of Solids. In this we are going to discuss the analysis of bars of varying sections. Okay. So here you can see a 3 bar which is acted upon by a load P on both the ends. Let A1 be the cross-sectional area of the first bar and L1 be the length, and A2 be the cross-sectional area of the second bar and L2 be the length, and A3 be the cross-sectional area of the third bar and L3 be the length of the third bar. Now as you can see, the P is the axial load which is acting on the section, and let E be the Young's modulus of the material. Now we have to find out the deformation delta L for the total bars which is acted upon by a single load P on both the ends. Okay, so the as we know, sigma 1 is equal to P1 by A1, and strain which is E1 for the section 1 which is equal to delta L1 by L1. Similarly, sigma 2 is equal to P by A2 and E2 is equal to delta L2 by L2. And sigma 3 is equal to P by A3 and E3 is equal to delta L3 divided by L3. Okay. Now, we have to find the changing length for each individual section, and then finally add delta L1, delta L2 and delta L3 for the total extension. Okay, now the first changing length delta L1 for the section 1 which is equal to PL1 by A1E, and for the next section delta L2 is equal to PL2 by A2E. Since E are common for all the sections and P and E are same for all the section, and L1 and A1 is varying. Okay, so delta L2 is equal to PL2 by A2E and delta L3 is equal to PL3 divided by A3E. So for adding delta 1, delta L1, delta L2 and delta L3, let's take P by E outside. So the final expression will be P by E into L1 by A1 plus L2 by A2 plus L3 by A3, where Young's modulus is same for all the sections. And if Young's modulus is different for all the sections, we cannot take E outside. Then the equation will be P L1 divided by A1 E1 plus L2 divided by A2 E2 plus L3 divided by A3 E3 will be the equation for total deformation of the section. Okay, now let's discuss a problem. Question number 1. An axial pull of 35 kilonewton is acting on a bar. The modulus of elasticity is 2.1 into 10 raised to 3 Newton per mm square. Determine the stress in each section and the total extension of bar. So in this question we have to find out the sigma 1, sigma 2, sigma 3 values, and also the total deformation delta L for the entire bar. Okay, and since the load P is given as 35 kilonewton, what is the equation for stress? Stress is equal to load divided by area. And you can see the diameters of each section. The first section diameter is 2 centimeter, next one is 3 centimeter, and third section diameter it is 5 centimeter. And the length of the first section, that is L1 is equal to 22 centimeter and L2 equal to 25 centimeter and L3 is equal to 20 centimeter. Okay, so we have all the values. Just find out the area of section 1, section 2 and section 3, and then divide load divided by pi by 4 into 2 square, load divided by pi by 4 into 3 square, and load divided by pi by 4 into 5 square. Will give the stress in each sections. So we have to we can find the values in terms of Newton per mm square, so convert all the areas into mm square. Okay, so you will get the value of sigma 1 is equal to 35 into 10 raised to 3, that is Newton, divided by 314.15 mm square. So the answer is sigma 1 is equal to 111.408 Newton per mm square for the section 1, and sigma 2 is equal to 49.51 Newton per mm square for the section 2, and sigma 3 is equal to 17.82 Newton per mm square for the section 3. And again the total deformation that we have to calculate. Since E is common for all the section, let's take P and E outside. So P divided by E into L1 by A1 plus L2 by A2 plus L3 divided by A3. So the total delta L is equal to 0.18 mm. Okay. Now, let's see another problem. A member formed by connecting a steel tube and aluminum bar are shown in figure. Calculate the magnitude of P, which is shown here, that will cause the total length of the member to decrease by 0.25 mm. Here the unknown term is load and the total extension it is given as 0.25 mm. The value of elastic modulus for steel and aluminum it is given as, for steel it is 2.1 into 10 raised to 5 Newton per mm square, and for aluminum it is 7 into 10 raised to 4 Newton per mm square. Okay, so here in this figure you can see the length of steel is 30 centimeter and length of aluminum is 38 centimeter, and the cross section of steel it is given as 5 by 5 and the aluminum cross section it is 10 by 10, which is acted upon by a load P. Okay. Now we have to find the value of P, and the total elongation delta L is given. So what is the equation for delta L? Delta L is equal to P into L1, P outside P into L1 divided by A1 E1 plus L2 divided by A2 E2. So L1 is given in the question, E1 is given in the question, and A1, and also L2, A2 and E2 is also given in the question. So the unknown term is P, and by simplifying this equation you will get the value of P as 224.35 kilonewton. Okay. Let's solve some another problem. Find the decrease in length of the steel bar as shown in figure. So here we have to find out the decrease in length since the load is in compressive in nature. So we have to find out the deformation delta L value again. Okay. So the equation for delta L is equal to, here you can see the two sections. So the equation will consist of two sections. So delta L is equal to P1 L1 divided by A1 E1. So or otherwise you can take P and E outside, since we cannot take P outside, and here we can take E outside since E is same for all the section. Okay, since P is inside the bracket, we can also put the E inside the bracket. So the equation can be written as delta L is equal to P1 L1 divided by A1 E1 plus P2 L2 divided by A2 E2. Okay, so here you can see in the first section it is acted upon by a load 2 kilonewton, and also here we can see the second section which is acted upon by a load 5 kilonewton. In addition to that, there will be this 2 kilonewton is also acting in this section. So while considering this second section of 15 mm dia, we have to consider the total load 2 plus 5, that is 7 kilonewton. Okay, so it is given in the question that the length of the first section L1 is equal to 180 mm and L2 is equal to 200 mm, and also the diameter of the first section it is 10 mm dia and the second section diameter it is 15 mm, and P1 which is equal to 2 kilonewton and P2 which is equal to 2 plus 5, that's equal to 7 kilonewton. Okay, now just substitute in the equation for delta L is equal to P1 L1 divided by A1 E1 plus P2 L2 divided by A2 and E2, A2 E2. Here E1 and E2 is same, but P1 L1 A1 is different for each section. Okay, so first of all P1 that is 2 into 10 raised to 3 Newton into L1 which is 180 mm divided by A1. We have to find the value of A1 by using the 10 mm dia by using the equation pi by 4 d square into E1 plus P2 L2 divided by A2 into E2. So that's equal to 0.0625 mm will be the total decreasing length of the bar which is acted upon by these two loadings. Okay. Since the total length of the bar it is given as, total length of the section it is given as 40 centimeter and L2 and L3 is equal. So L2 is equal to L3 is equal to 40 minus L1 divided by. So this is the question. A bar is subjected to a tensile load of 160 kilonewton if the stress in the middle portion is limited to 150 Newton per mm square. Determine the diameter of the middle portion, the length of the middle portion, and if the total elongation of the bar is 0.2 mm. Take E is equal to 2.1 into 10 raised to 5 Newton per mm square. Okay, so the length of the middle section can be assumed as L1 and the diameter it is D, and also the diameter of the first section which is given as 6 centimeter and the diameter of the last section which is given as 6 centimeter. Now the length of the first section which is L2 and the length of the last section which is L3. Okay. Now the total load is 160 which is given, and also the stress in the middle portion is also given, that is 150 Newton per mm square. So stress is equal to load by area. From that we can find out the value of diameter at the middle section. And also we have the equation for deformation delta L for the entire section, and is also given, and just by expressing L1 in terms of just by expressing L2 and L3 in terms of L1, you will get the values of L1 first and then you will get the values of L2 and L3. Okay. Now let's discuss a problem on the analysis of uniformly tapered circular section. So the uniformly tapered section means the section which is having the diameter which is reduced from D1 to D2. Here you can see in this figure the diameter of the circular section which is decreases from D1 to D2. So the equation for delta L is equal to 4 PL divided by pi E into D1 D2, where 4 into P is the load which is acting on the section and L is the total length of the tapered circular section, and E is the Young's modulus, and D1 is the diameter at one end and D2 is the diameter at the other end. Okay. So let's do a problem. A rod which is tapered uniformly from 40 mm diameter to 20 mm diameter in a length of 400 mm. It is subjected to an axial load of 5000 Newton, and if E is equal to 2.1 into 10 raised to 5 Newton per mm square, find the extension of the rod. So you can all the dimensions are given such as D1, D2 and L, and P is given, and also E value it is given as 2.1 into 10 raised to 5 Newton per mm square. So just substitute in the equation for delta L is equal to 4 PL divided by pi E into D1 D2, where P is equal to 5000 Newton, L is equal to 400, and E is 2.1 into 10 raised to 5 Newton per mm square, and D1 which is 40 mm and D2 which is 20 mm. And finally you will get the equation for delta L is equal to 0.015 mm. Okay. Now find the modulus of elasticity for a rod which is tapered uniformly from 30 mm to 15 mm dia in a length of 350 mm. The rod is subjected to an axial load of 5.5 kN, and the extension for the load it is given as 0.25 mm. Here we have to find the value of Young's modulus capital E, and all other data are given. That is D1 is equal to 30 mm, D2 is equal to 15 mm, and L is equal to 50 mm, where P is equal to 5.5 kilonewton, that is 5.5 into 10 raised to 3 Newton, and delta L is equal to 0.025 mm. So here we have to use the deformation equation for a uniformly tapered circular section, that is delta L is equal to 4 PL divided by pi E into D1 D2. So from that find the equation for E, that is E is equal to 4 PL divided by pi into D1 D2 into delta L. Then substitute the values of P, L, D1, D2 and delta L, and finally you will get the value of Young's modulus E as 2.18 into 10 raised to 5 Newton per mm square. Okay. Let's see one another problem. A 1.5 meter long steel bar is having a uniform dia of 40 mm for a length of 1 meter, and in the next 0.5 meter its diameter gradually reduces from 40 mm to 20 mm. Determine the elongation of the bar when it is subjected to an axial tensile load of 160 kilonewton, given E is equal to 200 giganewton per meter square. Okay, so it is clear from this figure that for a length of 1 meter the diameter is uniform, and from by this point it reduces from 1 to 0.5. So from this section, that is for the second section, the diameter D1 is 1 meter and the the diameter D1 is 40 mm and the diameter D2 it is 20 mm. That is, the section 2 is a uniformly tapered circular section and the section 1 is a uniform cross sectional area, that is uniform circular cross section. Okay, so by considering as two individual section, let's solve the problem. Okay. So for delta L1 is equal to PL divided by AE, where P is 160 kilonewton and L it is 1 meter divided by A, it is pi by 4 into 40 square. So you will get the value of delta L1 is equal to 4 PL by pi d square, and which is equal to 0.6366 mm. Now consider the second section, which is a uniformly tapered circular section on which the diameter D1 is equal to 40 mm and D2 is equal to 20 mm. So use the equation delta L2 is equal to 4 PL divided by pi E D1 D2, where P is same load, that is 160 into 10 raised to 3 Newton, and L it is 0.5 meters, so 0.5 into 1000 mm divided by pi into E is 200 into 10 raised to 3 into D1 and into D2. So you will get the deformation as 0.6366 and add all the deformation, that is delta L1 and delta L2. You will get the total deformation for the entire section as 1.2732 mm. Okay. Now, so in the last section we discussed the analysis of uniformly tapered circular section. So here we are going to discuss the analysis of uniformly tapered rectangular section. Okay. So these are the equation for uniformly tapered rectangular section delta L. Delta L is equal to PL divided by E into T into A minus B into log of A by B, where A and B is A is the width at the bigger end and B is the width at the smaller end, and P is the axial load on the bar and L is the length of the rod, and E is the Young's modulus of the rod and T is the thickness of the rod. Okay. Let's do one problem. A rectangular bar made of steel is 2.8 meter long and 15 mm thick. Okay, here the length and thickness is directly given. The rod, which is subjected to an axial tensile load of 40 kilonewton, and the width of the rod varies from 75 mm at one end to 30 mm at the other end. Okay. Find the extension of the rod if Young's modulus is equal to 2 into 10 raised to 5 Newton per mm square. Okay, here the rectangular bar length, which is given as 2.8 meter, that is equal to 2800 mm, and the thickness, which is given as 15 mm, and which is subjected to an axial tensile load of 40 kilonewton, that is P is equal to 40 kilonewton, that is 40 into 10 raised to 3 Newton. Okay, so the width, which is varies from 75 to 30 mm, it is given in the question, that is A is equal to 75 mm and B is equal to 30 mm. Now, we have to find the value of delta L using the equation PL divided by ET into A minus B into log A divided by B. Okay, so substitute all those values, that is P is equal to 40 into 10 raised to 3 into length, that is 2800 mm, divided by E into T, that is 2 into 10 raised to 5 into 15 mm, into A minus B, that is 75 minus 30 into log to the base E 75 divided by 30, so which is equal to 0.760 mm is the answer. Okay. Now another question. The extension in the rectangular steel bar of length 400 mm and thickness 10 mm is found to be 0.21 mm. The bar, which is tapered uniformly in width from 100 mm to 50 mm. If E for the bar is 2 into 10 raised to 5 Newton per mm square, determine the axial load on the bar. So the length, which is given as 400 mm and thickness, which is given as 10 mm, and deformation delta L is equal to 0.21 mm. So the width, which is varies uniformly, that is A is equal to 100 mm and B is equal to 50 mm. E is also given as 2 into 10 raised to 5 Newton per mm square. We have to find the axial load on the bar, that is P. So P, which is equal to delta L into ET into A minus B divided by L into log of A by B. Just rearrange the equation for finding the value of load. So you will get the value of load, which is equal to 75.741 kilonewton. Okay. Now Let's discuss the another problem, that is analysis of bars with varying loads at the ends. And till now we were discussing about the bars which is having a constant load on both the ends. Now the load which is going to vary on one end and the other. So till now we were discussing the bars with same load at the ends. Now we are discussing the bars with varying loads at the ends. So read the question. A brass bar having a cross-sectional area of 1000 mm square is subjected to an axial forces as shown in figure. Find the total changing length of the bar. Take Young's modulus is equal to 1.05 into 10 raised to 5 Newton per mm square. Okay. Now the cross-sectional area of all the sections is 1000 mm square and is subjected to different sets of forces as shown in figure. So we have to find out the value of total changing length, and E is also given. So we have to consider the each section individually, that is AB, BC and CD, and then we have to make the loads on both the sides should be equal. We have to make it like that. Okay. So first of all, consider the section AB. So it is given that the on the left end A. So the same load 50 kilonewton will be acting on the right end. Okay, by calculating delta L is equal to PL by AE, you will get the value of delta L. A is given, and P you take it as 50 kilonewton and length which is 600 mm is also given. And since the load is tensile in nature, we can consider it is positive. That is deformation is elongation which is 0.286 mm. Now at B we just took only 50 kilonewton, but there is the actual load is 80 kilonewton given in the question. Okay, so we have to consider the remaining 30 kilonewton which is acting towards right. We have to consider, or by expressing it is in a mathematical way, we can show that 50 plus x is equal to 80. 50 means we took it as positive since it is acting towards right, and 50 plus h, that is an unknown term, which is equal to 80 kilonewton. That is a total load which there exists, and which is also I put it as positive since it is acting towards right. Okay, so h is equal to 80 minus 50, so 30 kilonewton acting towards right should be marked from the next section B. Since the 30 kilonewton is marked here, it is compressive in nature. We have to the same time we have to mark the 30 kilonewton compressive in nature at the section C. Okay, so now you can consider the section BC, and where load P is equal to 30 kilonewton, that is 30 into 10 raised to 3, and L is 1000 mm divided by A into E, you will get the value of delta L for the section BC, and which is equal to minus 0.26 mm. It is compressive in nature. Okay, that's why I put the negative sign. Now at C, the total load is minus 20 kilonewton in the question, but we already used minus 30 kilonewton. Okay, so the remaining is minus 30 plus x is equal to minus 20. That is x is equal to 10 kilonewton, which is positive, that is acting towards right. Consider all the forces acting towards left as negative and all the forces which is acting towards right as positive. So x is equal to 10 kilonewton, compressive in nature. So you will get the value of delta L by using the expression PL by AE, and which is equal to minus 0.114 mm. So the total changing length delta L is equal to 0.286 minus 0.286 minus 0.114, which is equal to minus 0.114 mm. Okay. Now another question. A member ABCD is subjected to point loads P1, P2, P3 and P4 as shown in figure. Calculate the force P3 necessary for equilibrium if P1 equal to 120 kilonewton, P2 equal to 220 kilonewton, P4 equal to 160 kilonewton. Determine also the net changing length of the member and consider E as 2 into 10 raised to 5 Newton per mm square. So at equilibrium, the total load acting towards left is equal to total load acting towards right. Okay, since the total load acting towards left is 120 plus P3, and that's equal to 220 plus 160. So P3 we have to calculate. P3 equal to 380 minus 120, which is equal to 260 kilonewton. Now we have 3 sections and the cross-sectional dimensions are given, length are given, and the different loads are given. So by considering each individual sections, we have to find the value of delta L for each individual sections. Okay. So first of all, consider the section AB. So here you can see the load which is acting towards left, it is 120. So the same load should be shown here. So I marked it as 120 kilonewton. So the load which is 120, then delta L is equal to PL by AE, that is 12 into 1000 into 0.75 into 1000 divided by A into E. You will get it as 0.281 mm. It is tensile in nature, so it is positive. Now consider the section BC. I took 120 kilonewton, so the remaining 100 that we have to mark here. So it is acting towards right, that means compressive in nature. So 100 will appear on both sides. So the delta L is equal to minus 0.8 mm since it is compressive in nature. Okay. Next section, which is CD. That means at C there was a total load of minus 260, that is towards left side. So we have to consider the minus 260 is equal to minus 100 plus X, that is X is equal to minus 160. That means a 160 load which is acting towards left side is marked at the NC. The similar load value, that is 160, should be marked at the right side, which is tensile in nature. So the delta L is equal to PL divided by AE, and that's equal to 1.0667. And since it is tensile in nature, it is positive. So the total deformation delta L is equal to 0.281 minus 0.8 plus 1.0667 mm. So that's equal to 0.55 mm. Okay. So that's the total deformation of the entire section. So till now we discussed about the analysis of bars of tapered, uniformly tapered circular section, uniformly tapered rectangular section, then the deformation for axially loaded bars and deformation for axially loaded bars with varying cross sections. Okay, hope you all understood these sections. Thank you.